Recent images captured by the James Webb Space Telescope have astonished scientists. Rather than enhancing our grasp of the universe, these visuals revealed a disturbing reality. Our existing understanding is insufficient to comprehend the concept of the universe in its early phases, where the theory of the Big Bang reaches its limits. This prompts us to consider new theories regarding its origin. The question arises about how the universe was formed in detail, and why this new discovery challenges even the most seasoned researchers to explore more about the Big Bang and the intricate nuances of this finding. Let's revisit the concept of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Instead, it was space itself that began, approximately 13.8 billion years ago, along with matter and time. From a singular point in physics and cosmology, a singularity refers to locations where gravity is so strong that the curvature of spacetime becomes infinite. Today, after billions of years since the universe's inception, we observe that our vast home is part of a fundamental cycle. For specialists, this reflects a natural aspect of the universe since its very existence. It appears to be in an endless expansion. However, it's crucial to understand that the universe isn't moving into prior space. Rather, space itself is perpetually enlarging. According to current theories, the first stars began to illuminate somewhere between 200 and 300 million years after the Big Bang, marking the conclusion of the so-called Dark Age. This was when the initial luminous celestial bodies clustered together to form mature galaxies. However, how swiftly these galaxies developed remains an unexplained enigma. A significant piece of evidence emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts reported that the telescope had detected numerous galaxies, some of which had existed around 300 million years after the universe's creation. However, compared to the cosmic structures that formed much later, these early galaxies were notably smaller and less massive. This fits perfectly with the scientific model accepted by researchers. The density of matter in the young universe was simply not sufficient to give rise to galaxies the size of those observed today. What began as the discovery of 6 luminous, red-shifted spots from the James Webb Telescope ultimately triggered one of the most significant cosmic crises in recent times. Although these newly found galaxies are comparable in age to previously recorded galaxies, they are nearly as large as our own Milky Way galaxy. This has created an intriguing mystery in galactic exploration. After examining a series of images captured by the near-infrared camera, specialists identified the aforementioned light sources using redshift. Researchers determined that the light from these objects took more than 1 billion years to reach our eyes on Earth. Therefore, we are dealing with structures that had already existed between 570 million years after the so-called Big Bang. By analyzing the characteristics of these structures, it was concluded that the Webb telescope had captured 6 very early galaxies in the images. Shockingly, these galaxies were so massive that they challenged conventional assumptions in cosmology. Rather than discovering the typical dwarf galaxies, structures were identified that were nearly as massive as our Milky Way galaxy, despite having formed early in the universe's history. If we continue to examine the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly exceeding the 10 billion solar mass threshold. However, regardless of whether this possibility is considered, the mystery isn't entirely resolved. Even in this case, there would be significantly more cosmic mass in the early universe than previously anticipated, presenting a riddle. The identified objects contradict nearly all traditional cosmological hypotheses. Even if only one of these galaxies proves to be real, it would challenge our previous assumptions. Moreover, the density of matter in the early universe would have had to be several times greater than previously expected to explain this phenomenon. Another equally puzzling explanation hinges on the notion that these galaxies formed in a way that remains entirely unclear to us. These revelations and the discussion surrounding the Big Bang are prompting more scientists to move away from this hypothesis. Many astrophysicists with alternative views feel their perspectives are not being acknowledged in scientific journals. Even those who express doubts about existing theories are often branded as baseless whims. However, it is evident that even scientists who still support the Big Bang hypothesis are continuously confronted with questions lacking definitive answers. These inquiries include specific issues such as why and how, 13.8 billion years ago, something literally emerged from nothing. Could something truly ever arise from nothing? Or was there some triggering event? Or was it all mere coincidence? Steven Weinberg noted that the concept of time, as we know it, began only with the Big Bang. Consequently, this process could not have been initiated by something external. A similar controversial inquiry relates to the uniformity of radiation and density throughout the universe. Regardless of which direction or at what distance we observe on a larger cosmic scale, we discover similar densities and distributions of galaxies, nebulae, and radiation everywhere. Moderate researchers explain this phenomenon through the theory of cosmic expansion. However, different specialists extend this assumption further with a theory of tumultuous expansion. According to this idea, inflation has only ceased in specific regions, like bubbles, and continues infinitely elsewhere. This suggests that numerous universes could be forming in these bubbles, each with its own individual physical laws. Within this framework, a major question arises. What if the universe doesn't represent the complete whole? More intriguingly, what if another universe existed before our own? In that case, the Big Bang would become part of a larger cycle. According to this viewpoint, our universe is part of a broader, multifaceted structure. Within this model, the idea of an eternal pattern of collapse and resurrection of the universe is proposed. However, this is not the only perspective presented in the realm of cosmology. Apart from the theory of the universe's origin, in 1955, for instance, an article appeared in NASA Spacetimes arguing that there may have never been a Big Bang, since the universe has existed for an infinite duration. In this view, the expansion of the universe would be non-existent, and the continuous arrangement of matter could give the impression of a consistent expansion. However, another fascinating hypothesis arises from the realm of quantum physics and string theory. Some experiments have suggested that our universe, and everything within it, could simply be a flat 3D image projected onto a surface. Consequently, there is a possibility that our world is a consequence of a higher simulation. While this might sound like the plot of a whimsical sci-fi film, it may indeed relate to the Kessler scale, which measures the degree of advancement of a civilization according to its ability to harness energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire universe, it might have created an ideal simulation. Nevertheless, understanding reality in such a scenario is an extremely complicated matter. Investigating the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited discussions about the very fabric of our reality, testing established theories and prompting researchers to reevaluate fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of how things came to be, a foundation of modern cosmology. According to this hypothesis, around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, expanding rapidly and giving rise to space, time, and matter as we know it today. This astronomical event is not just an explosion within pre-existing space. Rather, it encompasses the very beginning of space itself. The idea of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this primordial epoch. The identification of early galaxies by the James Webb Telescope calls into question our beliefs about the speed at which structures emerged in the universe's formative years. These galaxies, discovered within a few 100 million years post-Big Bang, seem astonishingly sophisticated and massive, defying predictions based on existing cosmological frameworks. A significant issue raised by these findings is the idea of cosmic expansion. The dominant theory posits that expansion took place within fractions of a second following the Big Bang, leading to a dramatic increase in the universe's size. This swift expansion could account for the uniformity of the cosmic microwave background radiation detected throughout the universe today. However, the recent findings imply complexities in the early universe's evolution that might necessitate revisions to inflationary models. The emergence of galaxies, like those observed by the James Webb Telescope, urges cosmologists to reevaluate the conditions and cycles that dictate the universe's initial development. These galaxies, now considerable in scale and mass shortly after the Big Bang, suggest a matter density that surpasses previous assessments. The enigma deepens when contemplating how such substantial structures could arise and develop in a relatively brief span of cosmic time. Furthermore, the discovery of these early galaxies provokes fascinating inquiries about the nature of dark matter and dark energy, two elusive elements that make up most of the universe's mass and energy content. While dark matter is thought to provide the gravitational framework essential for galaxy formation, the distribution and characteristics of dark matter in the early universe remain unclear. In light of these astrophysical enigmas, theoretical physicists are investigating alternative cosmological models that contest the traditional Big Bang perspective. Some theories propose that our universe is merely one among many in a vast multiverse, each with its own unique physical laws and constants. These concepts, arising from progress in string theory and quantum cosmology, suggest a more intricate and interconnected universe than previously imagined. One increasingly popular notion is eternal inflation, where universes continuously emerge from a larger inflating space. This hypothesis implies that our universe could be just one bubble among countless others, each with its distinct attributes. The challenge lies in obtaining observational evidence to support such theoretical concepts as they push the boundaries of empirical validation. Another intriguing speculation is that our universe exists within a simulated reality, similar to a computer-generated environment. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable accuracy. If true, our perception of reality as a separate physical universe could be fundamentally transformed, raising significant philosophical and scientific questions about the essence of existence. Moreover, advancements in observational astronomy continue to reveal the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its extraordinary sensitivity and resolution, promise to uncover even more mysteries of the cosmos. Future observations may shed light on the universe's earliest moments, offering insights into its ultimate destiny and the fundamental principles that govern its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The pursuit of unifying gravity with the other three fundamental forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central aim of theoretical physics. Concepts such as quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the domain of quantum mechanics, the very idea of time remains a topic of intense discussion. The notion of time as a linear progression from past to future is challenged by quantum theories suggesting that time may be emergent or even elusive at a foundational level. Understanding the nature of time within cosmological models could revolutionize our comprehension of the universe's origins and evolution. Additionally, the quest for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's examination of exoplanet atmospheres, may yield evidence of biosignatures indicative of life beyond Earth. Alongside these scientific endeavors, social and philosophical reflections on the universe enhance our understanding of our place within it. Questions regarding the significance of existence, the likelihood of intelligent life elsewhere, and humanity's future in space exploration inspire contemplation and discussion across various fields. As we stand on the brink of a new era in astronomy and cosmology, fueled by technological advancements and theoretical breakthroughs, we are reminded of the profound interconnectedness of everything, from the tiniest subatomic particles to the immense cosmic structures spanning billions of light years. The universe reveals its secrets to those willing to explore and question. In conclusion, the investigation of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The insights gained from instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and provoke new inquiries regarding its evolution and development. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic expansion, we move closer to a broader understanding of the universe and our role within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a monumental quest to decode the cosmos, a mission that promises to redefine our understanding of existence itself. Whether exploring the depths of black holes, mapping the paths of distant galaxies, or contemplating the nature of reality, each discovery brings us nearer to unraveling the intricate tapestry of the universe. As we venture deeper into the cosmos, guided by curiosity and driven by a desire to comprehend the universe's vastness and intricacy, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment embodies the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. Thus, the exploration of the universe is not merely a scientific endeavor but a profound human quest for knowledge and meaning, a journey that transcends the confines of space and time, inviting us to ponder our place in the grand tapestry of existence.